everyone, I'm Meghamala, working as Assistant Professor from Electronics and Communication Department, Institute of Aeronautical Engineering. So, coming to today's topic is about the instantiation of strengths and delays. So, before we go forward into our topic, let us discuss what are the strengths and delays. In the previous classes, already we have discussed regarding the delays. So, delays are meant with respect to the time constraints, isn't it? That means what? If, for example, if I'm considering a AND gate, a simple logic gate, AND gate, it has A and B as inputs and Y as output. So, when I'm propagating these two inputs A and B, they will be propagating their signal, or as a signal will go with some strengths and as well as some delays. For example, A is going forward with a delay of 10 nanoseconds. Usually will represent the delays in terms of hash and the number, the delay. And B is going with 20 nanoseconds of delay. So finally at the output, I will be observing my output at 13 nanoseconds of delay, isn't it? So Y is equals to 30 nanoseconds of delay. This is what I'm going to observe at the output. So coming to the strengths, the more the strength, the less the delays. And the less the strength, the more the delays will be. That means the both strengths and delays are inversely proportional to each other. So today's topic, instantiations with respect to the strengths and delays. The most general form of instantiation, strengths and delays can be combined. So usually strengths and delays, as I said you before, strengths and delays both are related to each other. They are inversely proportional to each other, as inversely proportional to 1 upon D. It means strength, if the strength is more, the signal strength is more maximum, then the delay would be minimum. If the delay is maximum, then the signal strength would be minimum. So here we see a relationship between the strength and delay. These two terms are not different. So here the strength and delays can be combined. For example, the instantiation. When it comes to the instantiation, this is what this is the NMOS transistor that I am considering. So for NMOS transistor, NMOS is a keyword. So in the previous classes also we have discussed many a times saying that the keywords plays a prominent role. Whatever the particular combination or logical sequential circuit that you are considering, always remember that the particular this keyword will represent the particular circuit. So here my circuit is, or else as being a designer, I am designing a NMOS transistor where my circuit is NMOS transistor. So my keyword goes with NMOS and then followed with the signal strength. So the strength here I am representing in terms of strong 1, strong 0. And obviously immediately I am representing the delays as well. So here when it comes to the delays, we have discussed there are 3 types of delays representation. The time delay would coming into the 3 times, that is TR, TF and TO. So TR is a rise time, TF is a fall time and TO is a turn off time. So the delays would be in terms of TR, TF and as well TO. So here in the instantiation, I'm giving the keyword first as NMOS. Why? Because I'm considering here NMOS transistor and then going on with the signal strengths. Here representing the strengths and here instantiating the delays. So how the strengths will be instantiated with respect to the strong, keyword strong 1 and strong 0. Okay, and then followed with the delays. So here I am representing the delays with respect to rise time, delay underscore R. So it is with respect to the rise time, delay R, and delay F. Delay F is with respect to the fall time, delay F, and then delay O. Delay O is with respect to the turn off time. So in the instantiation, first goes with the keyword and then followingly goes with the strength and then immediately follows with the delays. So after that, here the particular gate I am considering is logic gates. For any kind of gate, GG is nothing but here I have mentioned with GG, it means a logic gate. So here as I am considering an AND gate, I can write AND gate. Instead of GG, I can also write AND gate. Okay, and then this is the terminal list. So here in the terminal list will be writing first, or else the instantiation goes like with respect to the output first and then follows with the inputs. So here S1 and S2 are the signals, and control is one more signal that I have with respect to the particular gate. So this is all about the terminal list instantiation. And then it has strength strong 0 when in the low state, and strength 1 strong 1 when it is in the high state. So here this sentence is clearly stating about, here we have mentioned strong 1 and strong 0. Strong 1 is nothing but the state when it is in the high state. Usually we will represent the high state as 1 and low state as 0, isn't it? High state as H and low state as 0. So here I have a signal strength is represented with strong 1. So my signal is in the high state signal. So strong 1. And then follows with the strong 0. Strong 0 is nothing but the low state. Okay. Then when output changes from low to high, that is from 0 to 1. When the output changes from low to high, usually we will represent this as rise time. TR, rise time, right? So the delay pertaining to this rise time is nothing but delay R. Then when the output is changing from high to low, so 1 to 0, high to low, then we call this duration, we call this time slot as fall time. So in terms of delay, the fall time is represented as delay underscore F. And then when the output turn off, it has turn off delay. So here in this particular state where the switch is off condition, okay, when the turn off state, when the switch is in the turn off state, it means that it is in the off condition. So here we represent that particular delay as delay underscore O. So these are just the explanation of how the delays with respect to the rise and fall and as well turn off times. Okay. And then here in the previous section already we have discussed regarding the NMOS, PMOS and CMOS switches. The switching conditions of these three NMOS and PMOS, they are quite contrast to each other. That means what? When the control signal is 1, in the NMOS transistor, when the control signal is 1, then the switch goes to on state, on condition. And if the control signal is 0, then obviously the switch goes to off condition. This is regards to the NMOS transistor. And as well, if you look for the PMOS state, PMOS transistor, in the PMOS transistor, when the control signal is 1, then the switch goes to off condition, off state. When the control signal is 0, then the switch goes to on condition. So if you observe the CMOS and NMOS, the both transistors, they are contrast to each other. They are quite opposite to each other. And then here are NMOS, and already we have discussed regarding the NMOS, RNMOS, PMOS, RPMOS, CMOS and RCMOS. RPMOS, RNMOS and RCMOS, these are nothing but the resistive switches. Okay, so the mechanism, when it comes to the switching mechanism, both holds the same mechanism. So, but the representation is differs with when it comes to the resistive switches. So, RNMOS, PMOS and RPMOS switches, these two can instantiated in the general form in the same manner. So, here the switches pertaining to the resistive switches, RNMOS, RCMOS or RPMOS, these when you are considering such switches, the instantiation for such switches also replica, they are the same replica of the particular instantiation. There is no much difference you will find. And then the general instantiation for the bidirectional gates too can done similarly. So here R transistor, RPMOS, RNMOS and RCMOS, as these are the bidirectional gates, and the instantiation for this bidirectional gate are also same. There is no much difference we will find. And then coming to the primitive instances. So what are the primitive instances? As Verilog is a case sensitive language, it has some libraries. Verilog library. In the Verilog library, we have different types of primitives. Logic primitives, gate primitives, instances and so on. So here the primitive instances are nothing but Verilog has a number of built-in primitives. So in general, Verilog has 26 sets of primitives, logic primitives. Okay, so here as Verilog has a number of built-in primitives that models gates and switches. So these primitives are regarding with respect to the gates and switches. So the Verilog library, it has 26 sets of gate primitives and as well as the switch primitives. So here the syntax goes for the instances of the primitives like this: gate, type, and then here it regards to the strength, followed with the delays. So usually, as I said we will represent the delay in terms of ash and the nanoseconds, 10 or whatever the numbers. So 10 nanoseconds of delay. This is how we represent, and strength is represented with respect to the strong 1 or strong 0. So when it comes to the instantiation, it goes like this: gate, type, followed with the strength, and then followed with the delays. Here the instance name. So what sort of instance that you are considering, okay? And here that instance will have some range, right? So pertaining to that instance, the range would be initialized, and then the terminal list. In the terminal list, obviously the output terminals are instantiated first and then forward with the input terminals, okay? And then this is with respect to the gates. As I said the primitives are the 26 sets of primitives which are present in the Verilog library. They are in terms of gate primitives and as well as switch primitives. So the instantiation with respect to the gate primitives goes like this, and we will see the instantiation with respect to the switch primitives. So the switch, type, followed with the delay. So here when it comes to the gate and switch, the difference here is in the gate primitive, we will see the signal strength. The signal strength will be calculated. So in that regard, we are writing the strength over here. But in the when it comes to the switch primitives declaration, we don't have any strength to be declared. It only has the delays. Switch, type goes with the delay, and then instance name. Okay, the particular instance name and the range of that particular instance and the terminals. So here you have to ponder on one thing, that the difference between the gate primitives and the switch primitives is, in the gate primitives there is a possibility of instantiating or else there is initializing the strength of a signal based on the strength of a signal using a keyword strength, whereas in the switch primitives there is no need to initialize the strength of a signal. Only we will follow with the delays and then with the instance name, with the range, and then with the terminal list. Okay, and now coming to the description. So in the description, the built-in primitives can be instantiated in modules to create a structural description. So here, what does it this particular sentence says is, the built-in primitives, these built-in primitives can be instanced. So this is how the instantiation takes place. The built-in primitives like gate primitives and switch primitives, we will be instantiated in order to create a module pertaining to the structure of a particular module. So whole and soul, we are concentrating only on the structure description. Okay, the structure description would comes from the gate level abstraction. So as we have discussed previously, we have 4 types of descriptions, abstractions. One is behavioral modeling, data flow, gate level, and switch level. So these 4 are the modeling styles. So here in the description of the primitives, okay, pertaining to the switch and as well as the gate primitives, only just to create a structural descriptional, we are using this built-in primitives. Okay, the built-in primitives can be instanced in modules to create the structure of that particular module, and then structural description of the behavioral of the model. So here the structural description comes with gate level. Okay, there is some relationship between the structural description and the gate level description. Overall, we can achieve the structural description only with the help of the gate level. Okay, and the gate level, in the gate level we can see the data flow, how the data flow modeling takes place. So these are all interrelated, but among this four of the modeling styles, we see the highest abstraction goes with the behavioral modeling. Okay, the behavioral, another name for the behavioral modeling is algorithmic modeling. So here the highest abstraction goes with the algorithmic modeling, but the rest of the three modelings are interrelated to each other. So here the Verilog has the built-in primitives. How these primitives will help us is just to create some structures. The module that you are considering, to create the structure of that particular model and the behavior of that particular model can be achieved with the help of the built-in primitives. So here, coming to the strengths and delays, we will see the strengths. Here, first row is about the name of the primitives, and then goes with the gate type, and here we have the terminal list. So here, coming to the logic. So here in the logic, we have the gate types. We can achieve the logic of a particular gate and NOR, and these are the basic gates we know. And for this basic gates in the terminal list, the instantiation of the particular things we have to write down the initialization of a things will be occurred. That is inputs and as well as the outputs. When it comes to the buffer and inverter, in these two gates as well, we have to write in the terminal list output and inputs are need to be initialized. And then tri-state logic. What are this tri-state logic is? Buff if 0, buff if 1, and not if 0 and not if 1. These three are nothing but the tri-state logic. Why this tri-state logic is? Usually this is what the NOT gate. This is nothing but the NOT gate, right? So here for this tri-state logic, the one more signal is to be considered. This is the control signal. Okay, so the control signal, whenever the control signal is the output, always it drives the output will be driven only with respect to the control signals and as well as the input signals. Whenever the enability of the control signal is, the output is based only on the enability of the control signals with regards to the input. So here in the terminal list for such kind of logic gates, that is tri-state buffers gates, the initialization in the terminal list goes with the input, output, input and as well as the enable. In the enable, usually we will write the control signal, CTRL. Okay, and then pull up and pull down resistors. So for this pull up and pull down, the gate type is pull up and pull down. For pull up, usually when the output goes from the high to low, if it is from high to low, then it is a pull up. When it is from low to high, there is a pull down transistor. And here in the output terminal will represent only, in the terminal list will represent only the output. This is all about the gates, gate primitives. In the gate primitives, these are the things we will observe. And when it comes to the switch primitives is regarding the all kinds of switches. So here we know MOS switches and CMOS switches. In the MOS switches, basically PMOS and NMOS switches that we consider, and CMOS is a complex metal oxide semiconductor switch. So here it is a combination of both P and N types. Okay, when these two switches P and N types are connected to parallel to each other, then it's nothing but a CMOS switch. So here in this MOS switches, we see NMOS, RMOS, RNMOS and RPMOS, both the resistive switch and as well as the normal switch. And in the terminal list, we will be representing the input, output and as well the enable, the control signal. And when it goes with the CMOS switch is nothing but it is RCMOS. Usually the keyword that we represent is CMOS or RCMOS. If you are considering being a designer, if you are considering any CMOS transistor, then your keyword must goes with CMOS. Okay, CMOS with strength and with delay and with the gate that you are considering and the terminal list. In the terminal list, first CMOS, these are the things to be enabled. Why? Because in the CMOS, when you are considering a CMOS switch, always remember that CMOS is nothing but it is a combination of PMOS and as well as the NMOS transistor. When the PMOS and NMOS, they both are, if they both are connected parallel to each other, then that structure is nothing but the CMOS. So here in the terminal list, for with respect to the CMOS transistor, you have to represent the output and input and the control signal. So here, as it is a combination of two switches, PMOS and as well as the NMOS. So here you have to write the P control signal and as well as the N control signal. That's how we are representing N enable and P enable. That means what? P control and N control. Okay. Then goes with the bidirectional pass. So here in this bidirectional pass switch, usually we will write the tran and rtran. Okay, and then the output that in the terminal list, the initialization of the terminals, output and input terminals would be represented when it comes to the bidirectional passes is in out and in out 1 and in out 2. And then bidirectional pass with controls lines. If it is with control lines, then we represent with respect to tranif 0, tranif 1, rtranif 0 and rtranif 1. And in the terminal list, the control signal would be initialized. Okay, so this is how this is an important table to be remember when you are asked to write a program based on a different switch or else based on a gate, the instantiation of a gate and the switch with respect to the strengths and delays. Then the table will help you to remember and to write the instantiation program clearly. So here, only gate primitives may have driven strength. So as we discussed in the previous slides, only pertaining to the gates, only the gates will have the strengths. The strength keyword would be represented only with respect to the gates, not with the switches. And then switch primitive pass the input strength to the output. So here, why we don't have the strength in switch primitives is what the switch will do. The switch will pass the input, it will pass a source from the it will pass the output from the input to the output. That means what the signal strength will goes from the input towards the output, right? So that's the reason the signal strength is not to be mentioned in this particular switch primitives. And then resistive switches, it reduces the strength as it passes through. So when it comes to the resistive switches are nothing but RNMOS, RPMOS and RCMOS. So these are nothing but the resistive switches. So these resistive switches will reduce the signal strength. So regarding as the resistive switches, we are concentrating on the switches, right? So switches, they don't have the signal strength. So in the case of the resistive switches as well, the signal strength, it would be the strength of the signal would be reduced when it passed from the input to the output. And then the delays represents the propagation delay through a primitive. So here the delays, it's very prominent to represent the delays in both the cases, in both the primitives, in the gate primitives and as well as the switch primitives. So here the delay representation, propagation delay takes place with respect to the delays, right? So obviously we will be represent or else we will initialize a delay in both the primitives as well as in the gate and switch. Then the default delay is 0. By default, the delay would by default the delay, it starts with the 0, 10, 20 and so on. So this is about the strengths and delays, representation and initialization pertaining to the terminal list and the category that you are considering, gate or switch, and the name of a logic. So here in the example, we see example is AND gate U1. So the U1 is the name of a gate that I'm considering, and here in the terminal list we are representing the output Q first and AB input terminal select. So this is how A, B and here it is a Q. Okay, and then AND gate, this is nothing but the delays. So when it comes to the delays, how am I representing? And the delays goes like this. So input is going with 2.1 and one more input is going with the 2.8. Okay, and then get QAB. Okay, this is with respect to the delay. And then will comes with respect to the strengths. So here the strength of a signal and pull 0, strong 1. So here I am considering the pull up transistor pull 0, Okay, that means what? The state is going from the high to low, isn't it? From high to low, that's the reason it's a pull 0, and the strength is strong 1. Okay, as it is going from the high to low, so it is a strong 1. Strong 1 means what? Always a state goes with respect to the 1, that is high. 1 is equals to high. So here QAB. So this particular example, it is helping us to analyze how to write a program with respect to the delay, with respect to the strength and the initialization of a particulars clearly. So here the initialization is taking place with respect to the input and output in the terminal list, and here the second statement is talking about the delays. The initialization of the delay, the representation of a delay with respect to the both inputs A and B are 2.1 and 2.8 nanoseconds. And then the third one is instantiation, or is the initialization of a particular strength. So how the strength, signal strength is initialized. Here pull 0 or strong 1 with respect to the QAB. So this is a basic example in the exam point of view. If you write such examples, you'll get good marks. And then coming to the switch primitives. So how these switch primitives are, what are these switch primitives, we'll discuss. The instantiation, so here particularly I am considering the NMOS transistor. So for this NMOS transistor, I have to consider the keyword NMOS. So the instantiation NMOS of gate 1 is out, in and control. So this NMOS transistor, it has the output, input and as well as the control signal. So has no delay associated with it. So here if you observe here this NMOS, basic NMOS transistor switch, here in this NMOS transistor switch you will see like we would observe only the keyword followed with the terminal list. Here we don't see any kind of delay representation. How we'll see the delay representation? For example, NMOS hash 20 and out, in and control. If such kind of initiation if you observe, then we say that there is some delay. Okay, if this instantiation, this particular switch is associated with some delay, isn't it? That's how we will represent the delay. Here when it comes to this particular example, there is no particular delay, so it has no delay associated with it. And then the instantiation of NMOS keyword goes followed with the delay and the gate that you are considering and the terminal list. So in this particular example, we see that they have, like we have a delay 1. So this instantiation, this NMOS transistor switch, it has a delay 1, as a delay for the output is to rise, fall and turn off. So as the delay, we can consider in 3 terms: delay for the rise, and delay for the fall, and delay for the turn off time. So here we have a delay 1, right? So this particular instantiation, the NMOS transistor, if we have a delay, right? So it is associated with some delay, and then delay 1 as a delay for the output. So such delay it could be with respect to the rise time, fall time and as well as the turn off time. And then we'll go for the third one. So here if you observe, we have 2 delays. In the previous example of the first one, for example, if you consider this as the first one, the second one and third one, in the first one we see that there is no delay. Okay, the switch is passing on with no delays, and whereas with the second, the switch has only 1 delay. The representation of delay 1 is like this, and the third case we see the delays of 2 delays. The representation, or else the transistor passing with the 2 delays, right? So how we represent is delay R and delay F followed with the gate and the terminal list. So here it has delay R as rise time, and as well as delay F as the fall time. Okay, so delay as rise time for the output and delay F for the fall time for the output as well. And here the turn off time is 0. So here there is no delay with respect to the turn off time. So the turn off time here is obviously 0. So this is how the instantiation pertaining to the delays goes like this. If there is no delay, simple logic is write down the NMOS keyword followed with the terminal list. If there is a present of 1 delay, then goes with the N keyword followed with the delay 1 and then the gate that you are considering, and goes with the terminal list. And if you have any 2 delays, okay, if you have any 2 delays, goes over with the key, start with the keyword goes with the delays, both the delays, and then gate, instantiation, and then initializing of the terminal list. In some cases, you may go for the 3 delays as well. So, in the when it comes to the 3 delays, regards to 3 delays, how can I write? NMOS, delay, R, delay, F, delay, turn off, and then the gate that I'm considering, GG, and the terminal list. So here in such kind of delays, so here totally I have 3 delays, right, with respect to rise time, fall time, and turn off time. So this is how the instantiation of the switch primitives goes with respect to the delays. And then coming to the NMOS delay. So here in this NMOS delay, we see delay R, delay F, and delay 0. So as I said you example, right? So here we have totally 3 delays. This is the 4th one. So totally we are representing with the 3 delays: rise time, fall time, and turn off time. So here when the control signal goes from 0 to 1, okay, when the control signal goes from 0 to 1, the delay can be assigned to the other unidirectional gates in the similar manner. So here in the switches we have unidirectional gates and as well as the bidirectional gate. So the delays can be associated. How they are associated with respect to the bidirectional gate, the same fashion they can be associated with respect to the unidirectional gates as well. And then the bidirectional switches do not delay transmission. Their rise and fall times are 0. So here in the bidirectional switches, okay, so here in the bidirectional switches, RMOS, RNMOS, RPMOS, and RCMOS, these could be considered as a bidirectional switches. So these bidirectional switches, they do not delay transmission. Okay, so switches do not delay transmission. How? With respect to the rise time, fall time, and turn off time. So the bidirectional switches, they do not delay the time constraints. Whereas when it comes to the unidirectional switches, we can see the time constraint delay would be observed. And they can only turn on, turn off delays associated with 0. So when it comes to the bidirectional switches, we don't see the delays with respect to the rise time, fall time, and turn off time, but they can associate it with turn on and turn off. That means what? Only the switches. If it is a high, the output is high. If the control signal is 1, pertaining to the NMOS transistor, if the control signal is 1, then the switch goes to on, turn on time, turn on condition. And when control signal is 1 in the PMOS transistor, and it will goes to off state. So this is nothing but the turn off condition. This is with respect to the PMOS and this is with respect to the NMOS. So here, as these are the bidirectional gates, so only we can see the 2 states, 2 conditions, either if it is turn on, turn off, or else if it is turn off and turn on. But whereas it comes to the unidirectional gates or switches, we can see the delays would be with respect to the rise time, fall time, and as well as the turn off time. So here, TRAN has no delay associated with it. So here, as we have discussed in the switches, bypass bidirectional pass transistors. So TRAN 1 and TRAN 0. So TRAN 1 and TRAN 0, these are nothing but the bidirectional pass transistors. So this bidirectional pass transistors, here these such kind of switches, bidirectional pass switches, they are not associated with any kinds of delays. So here we will see the TRANIF 1. So the delay TRANIF 1, delay R and delay F. So these are the bidirectional pass switches. So these are bidirectional pass switches. So these are bidirectional pass switches, where these bidirectional pass switches, they don't go pertaining to the switches in the instantiation of particular keywords, delays, strengths, and the terminal list. We see with respect to the switches, there is no signal strength is to be mentioned. Okay. So here, that's how there is no signal strength. As it is a switch, only will write with respect to the delays. So TRANIF 1, as it is a bidirectional pass switch, TRANIF 1, it has 2 delays, R and F, with respect to the rise and fall. And then GF is a primitive gate that you are considering, and terminal list. Terminal list as input, output, input, and as well as the control signal. So here, when the control signal, if it is changing from 0 to 1, so when it is changing from 0 to 1, obviously from 0 to 1, it says that the delay is a rise delay. Okay, this mechanism already we have discussed numerous time in the previous classes, and now also just for the example sake, I'm explaining again. So here it is, when the control signal switches from 0 to 1, then the delay is delay rise time. And when the control signal switches from 1 to 0, isn't it? So this is nothing but the turn off with the delay f. Okay, so here this is with respect to tranif 1, and now we'll see with the tranif 0, these here with 2 delays. Here this is with 2 delays, whereas here it is with 1 delay. So here in the 1 delay, tranif 1, delay 0, and the gate followed with the terminal list. So in the terminal list, output, input, and control. So it represents the instantiation with delay 0. So as a delay for the switch is turned on when the control signals goes from 0 to 1. So when the control signal goes from 0 to 1, the switch will be in the on state, and with the same delay it will turn off when it goes from 1 to 0. So here in this particular example, with respect to the rise time and fall time, there is delay R, rise delay and fall delay. In the rise delay pertaining to the delay 0. Okay, so here we are saying that is a delay 0. So here in this delay 0, the switch will be in the on condition only when the control signal is driven from 0 to 1. When the control signal is driven from 0 to 1, then in such cases the switch will be on. And when it is driven from the falling from the 1 to 0, then here the switch goes to off state, and you call that delay as the delay off. So here this example is with respect to the bidirectional pass switches. So in the bidirectional pass switches, there is no need to represent or initialize the signal strength. Okay, only with respect to the gate primitives, the signal strengths would be initialized. How is? Like gate strong 0 or strong 1, and then delay 1 and delay 0, and then goes with the gate and then the terminal list. Okay, so this is how the instantiation takes place with respect to the gate primitives. But whereas with respect to the switch primitives, remember that there is no need to represent the signal strength, only the particular gate. Okay, if it's a switch, NMOS switch, write down the NMOS switch, goes with the followed with the delays, and then immediately followed with the circuit that you are concerned, the name of a circuit, name of the instance, and then the terminal list. So this is all about the instantiation of the switches and as well as the delays. So here the important thing to be remembered is we have 2 types of primitives in the Verilog: switch primitive and as well as a gate primitive. In the gate primitive, we have to represent the signal strength, the strength of the signal. Okay, if it is 1 high, if the signal strength is high, we represent with the strong 1. If the signal strength is low, we represent with the strong 0. Okay, the signal strength would be represented only with respect to the gate primitives. When it comes to the switch primitives, we represent only the delays. Okay, so all the switches pertaining to the resistive switch or bidirectional switch and the normal switch and the CMOS switch, always in the switch primitives we represent the only the delays and followed with the name of the instance and as well as with the terminal list. So this is all about the switch primitives and as well the instantiation of the switches and signals as well as the delays. So, and this is the most important thing to remember. This table is very important to remember for the exam point of view, and as well this is also very important, the syntax with the primitive instances. So this is this particular syntax is very easy to remember. This is one with respect to the gate primitive and then with respect to the switch primitive. So here if you observe in the gate primitive, there is a necessity of writing the strength of a signal. Okay, strength. So here the strength of a signal will usually represent with the strong 0 and strong 1. Whereas with the switch primitive, okay, in the switch type, we represent the switch type followed with the delays. Okay, there is no need to observe, there is no need to initialize the strength. Only in the switch primitives, it follows with the delays, the instance name and the range of the instance followed with the terminals. So this is all about the instantiation of the switches and the gates. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.